Okay, so one of the cool things that we can do with these exponential functions is we can actually solve some problems involving exponentials. So, let's have a look at an example. So, we've got the volume V of a balloon in millimeters cubed as it expands over time at t seconds is given by V is equal to 3e to the power of 0.8t. What is the size of the balloon after 5 seconds? What is the rate, so dv dt, at which the size of the balloon is increasing, and show that dv dt is equal to 0.8 times v? At what rate is the volume increasing after 5 seconds? What is the average rate of increase over the first 5 seconds? When will the balloon reach a size of 85 millimeters cubed? And when is the balloon increasing by 650 millimeters cubed per second? Now, you guys already know how to do questions very, very similar to this, and you in fact know how to do most questions involving this sort of stuff. What I'm going to do is I'm just going to show you how this can relate to the exponentials now. So let's start with part A. So part A is, of course, what is the size of the balloon after 5 seconds? So what we're going to do is we're going to substitute our 5 into our equation. So V is equal to 3e to the power of 0.8t when t is equal to 5. So that's v is equal to 3e to the 0.8 times 5. And we're going to put that into our calculator, okay? Because we're actually going to get a value back out. So 0.8 times 5, and that gives us 100. So volume is equal to 163.79 to 2 decimal places millimeters cubed after 5 seconds. Okay, that's it. That's part A. Now part B says find the rate, so dv dt. So it tells you what to do. Find dv dt at which the size of the balloon is increasing and show that dv dt is equal to 0.8 times v. Now basically whenever we talk about rate in these types of questions, we're talking about the derivative. Whenever we're talking about just the volume or something, we're talking about the original function. If I'm asking when something's going to reach a size, volume. If I'm looking at a question like part F, where it has a rate, 650 millimeters cubed per second, derivative. So let's move on, go to part B. Okay. So what we're going to do is we're going to find what dv dt is. Okay, and then we're going to find dv dt. So if v is equal to, so what I should do is, in fact, I should write, so v is equal to 3e to the 0.8t. So dv dt is equal to, now remember the shortcut is that the derivative of this comes out the front. So it's going to be 0.8 times 3e to the 0.8t, because that's just the same. We could also do the chain rule to actually work out what that one is, but I don't think that's necessary. Now that's the first bit, but what we want to do is show that dv dt is equal to 0.8 times v. Well, what we can see is that here is just equal to v. So what we can say is, but v is equal to 3e to the 0.8t. So dv dt is just equal to 0.8 times v. And there you go. Nice and easy. Part C. Now part C says that at what rate is the volume increasing after 5 seconds? So rate means derivative at x is equal to 5. Okay, so dv dt is equal to 0.8 times 3e to the 0.8t. So at, or it should be not x, it should be t. That's my bad. So at t is equal to 5, we get 0.8 times 3e to the 0.8 times 5. Okay, so all I need to do for this one is just put 0.8 times at the front, and then we get 131.04 millimeters cubed per second. So that's the rate at which it's increasing. So it doesn't mean that it's going to increase by that much in a second. Well, it would mean if you were blowing at that exact rate. But remember, as it's an exponential, it's going to be increasing and decreasing depending on at what time you are blowing in at. Okay. Part E is when will the Part D is what is the average rate of increase? Okay, so what is the average rate of increase over the first 5 seconds? Okay, so D. So we know that after 5 seconds, the balloon's volume is equal to, and it is equal to 163.79. Okay, and that's millimeters cubed. At time is equal to 0, how much volume is in it at when time is equal to 0? Well, this is kind of a little bit deceptive because you would think a balloon would have no volume in it to begin with. But we need to actually use the equation. So volume is equal to 3 e to the 0.8 t at t is equal to 0. And v is equal to 3 e to the 0.8 lots of 0, which means that v is equal to 3 millimeters cubed. Now that might just mean in this case of this that there's a little bit of air already in there to begin with. And in most balloons cases, there's probably going to be something in there to begin with. So it's probably a reasonable amount. So the average is just the sum of the two, so 163.79. Plus 3 divided by the time it takes to get there, so 5. Or 5 plus 0. So 163 plus 3 over 5. So 166.79 divided by 5. And that gives us 33.358 millimeters cubed per second. So therefore, average in first 5 seconds is 33.3, not 5, 358 millimeters cubed per second. And there we go. So that's part D, find the average. Part E is to when the balloon, well, when will the balloon reach a size of 85 millimeters cubed? So that is when will V be equal to 85 millimeters cubed. Well, we know that the volume is equal to 3e to the 0.8 t. And what we can do is we can just substitute our V into this. Okay, so it becomes 85 is equal to 3e to the 0.8 t. Now to solve this, what we're going to do is divide both sides by 3. So divide by 3, divide by 3. It's going to give us 85 on 3 is equal to e to the 0.8 t. Okay. Now, do we remember how to remove exponentials? So the inverse of an exponential, remember, is a logarithm. So I'm going to take log of both sides. So log and log. And it's going to be the natural log because it's base e. So what this is going to give us is log of 85 on 3 is equal to, and this should be done in black because that's what I'm up to. So log of 85 on 3 is equal to the natural log of e to the 0.8 t, like that. Now remember the power of a logarithm rule. So the power rule is if you have a log a or b to the x, then that's the same as x lots of log a of b. So essentially if you have a power, you can bring it down the front. So this is the same as log of 85 on 3, which is equal to 0.8t log of e. Now we know that this guy here is equal to 1. So this is the same as log of 85 on 3 is equal to 0.8t times 1. So that's just going to disappear and we're going to be left with 0.8t. And then to get t by itself, I'll leave that on the same side actually. We're going to divide both sides by 0.8. So divide by 0.8, not 3. And that is going to give us our t value. So therefore, t will be equal to, I'm going to put this in, so log of 85 over 3, okay, close the bracket off, over 0.8. There you go, time will be 4.18 seconds. So therefore, it will take 4.18 seconds to get to 85 millimeters cubed. For the volume to get there, that should say. Okay, so that's part E. Let's go to part F now. Now, part F says, when is the balloon increasing by 650 millimeters cubed per second? So 650. So 650 millimeters cubed per second is a rate, and that means we want something to do with the derivative. Okay. So dv dt is equal to, now our derivative back up here, all the way back up here, was 0.8 times the function. So it's going to be 0.8 times 3e to the 0.8t. Okay. And we want when the rate is equal to 650. So what we're going to do is we're going to say, well, this is our dv dt. So we can substitute that in, just that bit there, times 3e to 0.8t. Okay, and we're going to follow the same steps as we did before because we had another exponential. So we're going to divide both sides by 0.8 times 3, divide by 0.8 times 3, in brackets by the way. So by doing that we get 650 over 0.8 times 3 is equal to e to the 0.8t. Okay, so again, we're going to take natural logs of both sides, so it's going to give us log of 650 over 0.8 times 3, and that's going to be equal to the natural log of e to the 0.8t. Okay, so remember our power of a power rule and the fact that the natural log of e is equal to 1. Okay, so we're going to have log of 650 on 0.8 times 3 is equal to 0.8t. Okay, so that means that t is going to be equal to the natural log of 650 on 0.8 times 3 over 0.8. So t is equal to, and then we're going to put this into our calculator. So it's 650 over 0.8 times 3. Okay. So this one's going to be a much bigger value because 650 is quite a bit. 0.8. So what this will do is this should give us the time in which it is increasing by that rate. Okay, so it's over 0.8, hit equals, and it's at 7 seconds. So what we can do is we can say that therefore the time in which the balloon is increasing at a rate of 650 millimeters cubed per second is at 7 seconds. And there you go. So that's an example of a worded problem. So again, it's just calculus that we know how to do already, and that's pretty much it, and we're going to leave it there. So what we're going to do now is we're actually going to move on to the extension stuff. Okay, so if you're not doing the extension course, obviously, then this will be the end of your exponential stuff until possibly year 12. Okay, but for us, and then you guys will move on to trig, I'm presuming, unless the scope has changed by then. So what we're going to do next is we're actually going to look at the extension side of exponentials. It's only a really short topic, but it is very, 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 very useful. So with that being said, that's going to be the end of this one. It's going to be the end of the advanced exponentials, and I'll talk to you guys soon.